Welcome to qnawire.
Hi, so in this case what we're going to have is different solution. In part A, we have a zero point 0.2 molar solution of HBr, that is a strong acid. So in order to calculate the pH, we can simply take the minus logarithm of the concentration, because remember that HBr in water, it is going to produce H2O plus Br minus. So the pH is equal to minus the logarithm of the concentration. So this is minus logarithm of 0.2, which is 0.1699 or zero point 0.7 if we round it up to the first significant figure. Next up in B, what we are going to get is a weak acid that has a concentration of 0.1 molar. This is formic acid. And it has a Ka equal to 1.9 times 10 to the minus 4. So remember that the concentration of H2O plus that we're going to have for a weak acid, when the concentration is much larger than the value for the Ka, is going to be equal to the square root of Ka times C0. This is going to give us a value for 4.36 times 10 to the minus 3 molar. Now, how can I relate this to the value of alpha? Well, we can look at our reaction. In this case, we have formic acid, HCHO2. When it comes into contact with water, it generates the formate ion, that is CHO2 minus plus H2O plus. Let's say that we have our ice table. Initially, we have C0. Water doesn't matter because it's a pure substance, and we have 0 and 0. The amount of change we're going to call it x. So an x portion, it is going to dissociate. That is going to give us the percent of dissociation. Over here we're going to have plus x and plus x. At the equilibrium we have C0 minus x, x and x. And this expression over here comes from the fact that we are considering the following equilibrium. The Ka is equal to the concentration of CHO2 minus the formate ion times the concentration of H2O plus divided by the concentration of my formic acid. Replacing the values at the equilibrium, this is x squared divided by C0 minus x. And we are assuming that C0 minus x is approximately equal to C0, right? Because the concentration is going to be much smaller than the Ka, and we expect the value for x to be as small. So essentially this value is the same as the x. So now how do I calculate the percent of dissociation? I'm going to take the value that actually dissociated, the x, divided by my initial concentration, and I'm going to multiply it by 100. So this is going to be x divided by C0 times 100. This is equal to 4.36 times 10 to the minus 3 divided by my initial concentration, that was 0.1 molar, times 100, giving us a 4.36%. Now, for the next case, in C, we're going to have a strong base, that is barium hydroxide. Oh, sorry. For the previous one, we also want to know the pH, right? And the pH is minus the logarithm of the concentration of H2O plus. And that concentration is the same as x, right? So the value that we get is 2.36. Okay, so this previous explanation applies the same for the weak base that we're going to do in the final step. So I'm not going to do all of the calculation again, but we can use it just for reference. Okay, now coming back to problem C, we have a 0.2 molar solution of this strong base. But remember that barium hydroxide Oops, sorry, the two on the wrong place. Barium hydroxide, when it comes into contact with water, it's going to dissociate as barium plus two equivalents of OH minus. So the concentration of OH minus that I'm going to have in solution is going to be equal to 2 times the concentration of barium hydroxide that I had initially. So in this case, this is going to be equal to 0.4. Now, the pOH is going to be minus the logarithm of the concentration of OH minus. So, minus the logarithm of 0.4, giving us 0.4, curiously enough. Well, 0.398, but we can round it out as 0.4. And we know that the pH plus the pOH needs to be equal to 14 when we are in aqueous media. So, the pH will be 14 minus pOH, giving us 13.6. Oops. And now for the final question, we have a weak base that has a concentration of 0.1 molar. This is ClO minus, and we're given now the value for Kb, that is 3.57 times 10 to the minus 7. The reaction that is going to occur, and in this case, you can calculate the concentration of OH minus. We're going to show that this is going to be equal to the square root of the initial concentration times Kb when the concentration is much larger than Kb. So the reaction that is going to occur is the following: ClO minus plus water is going to generate HClO plus plus OH minus. Sorry, I kind of bugged for a second. So if we write down our ice table in terms of concentrations, we have initial concentration. Water doesn't matter, 0 and 0. A portion, it is going to react, it is going to get associated with water. So plus x and plus x. And over here, we're going to have at equilibrium C0 minus x, x, and x. So the Kb for this reaction is defined as concentration of HClO times concentration of OH minus divided by concentration of ClO minus. This is equal to, replacing the values, x squared divided by C0 minus x. We do the same approximation, and we are assuming that C0 minus x is approximately equal to C0 because of the value of Ka. We assume that the value for x is going to be much smaller than C0. So, taking that into account, x is equal to the concentration of OH minus that we're going to find at equilibrium, and that is going to be equal to a square root of C0 times Kb, which is a square root of 0.1 times my Kb, that is 3.57 times 10 to the minus 7. Okay, so the value for x is 1.88 times 10 to the minus 4. This is going to be in molarity. Thus, the pOH, remember that this is the same as concentration of OH minus. The pOH is going to be the minus logarithm of that, giving us 3.725. And applying the same relationship as before, pH is equal to 14 minus pOH, giving a result of 10.275. And that is going to be our final answer. Thank you very much. Have a good one.